All right, so as you can see today, we're going to build on the background knowledge that we developed last week working with exponential functions, looking at some real-life application of exponential functions, looking at exponential growth and decay. Really simple to see some application in the real world, especially when you look at some science class, even look at some social studies and civics classes, as far as things that grow or decay exponentially over time. Kind of like what we talked about, these are not linear functions. You're not looking at a constant rate of change. And just like what we talked about in class with the population size of the world, as time goes on, that population steadily increases as a rate too. So we're going to talk about exponential growth and decay. You're going to have some equations to look at, some formulas to look at, some story problems to work. What you need out on your desk, you need a paper, you need a pencil, and you need your calculators, because there is some heavy-duty calculations going on. You'll probably notice when you get into algebra, the more real life it gets, maybe a little more difficult the math gets. So have a calculator ready to go too. First thing we'll talk about is exponential growth. It's just like it sounds. We're looking at something growing over a period of time, and as time goes on, that rate of change seems to increase, and it grows greater with time. Exponential growth can be modeled by the function y equals a times b to the x. Notice a has to be greater than 0. If a was 0, we would have some problems there where everything would become 0. And if a was less than 0, we're no longer looking at a growth situation. We need an initial amount that is greater than 0. And then b has to be greater than 1, because if it was less than 1, we'd be looking more at decay. So we need growth here. What you need to understand, the base in that situation is the growth factor. The way we figure out the growth factor is you start with 1, and then you add the percent rate of change expressed as a decimal. So something that you definitely want to either highlight or circle or underline in your notes is where this growth factor comes from. It's 1 plus the percent rate of change expressed as a decimal. That's what leads to growth. If it wasn't greater than 1, we would not have growth like we do. And so one simple way of putting it into your notes, y equals a times b to the x, where a is the initial amount, or what we have when x equals 0 before there's been any time that passes. And b is the growth factor, which has to be greater than 1. Definitely make sure you got this in your notes. The best example of real life exponential growth, other than maybe population size, something that would be very important to you financially down the road, is compound interest. Compound interest refers to when a bank pays interest not only on the principal or the amount that you put into the bank, but it also pays interest on the interest that they've already paid you. So basically you're making money on the bank's money. It's a great situation if you can find examples of compound interest, because as you can see, exponential growth means your money is growing exponentially. This formula is pretty complex. It says a equals p times 1 plus r over n to the nt power. And so we got to break that formula down. And if you haven't already started this, you're going to need it for the next problem, and you're going to need it quite a bit. This is the compound interest formula. What it basically means, A stands for what's in your account. A is how much have you earned up until this point. P is the principal, or what you deposit initially. R is the interest rate that the bank agrees to pay to you. N is how many compound payments there will be throughout the period, and then T is the number of periods. A way to simplify it in my language, again, A is the balance of the account, P is the initial deposit. The interest rate is given as a decimal, just like we've always talked about. We don't want to give it as an actual percent. And then N is the number of times interest is compounded per year, and T is the time in years. Make sure you have this formula in your notes. Make sure you kind of have the different parts of the formula in your notes as well, so you understand how to use it. This is where you're going to want your calculators too. A compound interest example. It says when Joe Bob was born, his parents deposited $2,000 in an account paying 4% interest compounded quarterly. What will the account balance be on Joe Bob's 18th birthday? Really, it looks complex, but truthfully, this is just substitution. This is something you've been doing for the last couple years. We're going to plug in some different numbers. Obviously, we want to know what the account balance will be, so the one thing we're going to be missing is the account balance. We're going to be missing the A. So we're just going to have A equals, and then we're going to plug in some different things for the P, the R, the N, and the T. Remember, P, if you go back to your notes, P stood for the principal, or the amount of the initial deposit. And as you see in the problem, his parents deposited $2,000. So in for P goes 2,000. Then we have some other numbers to punch in. We still have our 1, and now we need to have the interest rate expressed as a decimal over the number of compoundings per year. Remember, R is the interest rate, and N is the number of times it's compounded per year. The interest rate, hopefully you can catch that in here. It's 4% interest. Remember, we're not going to say 4. We need this as a decimal. 4% is a decimal, 4 out of 100. That would be 4 hundredths. The n number might be a little difficult for you to find if you don't understand what quarterly means, but just like there are 4 quarters in a basketball game, 4 quarters in a dollar, there are 4 quarters in a year. If you take the 12 months of the year and divide by 4, you'd have 3 months. So every 3 months, 4 times throughout the year, they're going to compound this interest. So our n in this case is going to be 4. It's done quarterly. And then we still have our exponent. N stays the same. N is 4. And t is the number of years, which in this case, if we want to know what it's going to be on his 18th birthday, t is going to be 18. This is what you'd want to write down to show your work. A lot of this we're going to do in our calculator, but a equals 2,000 times 1 plus 0.04 over 4 to the power of 4 times 18. Got to follow your rules of order of operations here. First thing we want to take care of is that stuff inside the parentheses, the 1 plus 0.04 over 4. So I'm just going to punch into my calculator 4 hundredths divided by 4 and just get that simplified for myself, and hopefully you can see that would just be 0.01. So really when I add 1 to 0.01, this amount right here is just going to be 1.01 or 1 in 100. Still have the 2,000 out front, and then we still have the exponent up there. 4 times 18 would be a way of simplifying that, which is 72. So now you're getting closer to where you have your answer for what his account balance will be. Now you just need to follow the order of operations again, and you need to ask yourself, would we multiply 2,000 by this first, or would we take care of the exponents first? And hopefully remember we take care of the exponents first. So in my calculator, I'm going to type 1 and 100th in parentheses. Then I'm going to use the caret key, which is just above the division symbol, to go to a power bigger than 2, and I'm actually going to take it to a power of 72. So when I take 1 and 100th to the power of 72, I actually get, when you repeatedly multiply that over and over and over again, I get 2.047099, etc. And I'm going to just round to the thousands place because I see a 0 after the 7. And so I'm going to have 2,000 times 2 and 47 thousandths. And so now, rather than round, I could just type the multiplication sign and then the number 2,000, and that'll give me the new account balance, which, as you see, because it's been compounded quarterly for 18 years, our $2,000 investment ends up being over $4,000 for Joe Bob on his 18th birthday. If I round that correctly, it looks like it's going to have about $4,094.20. So an example of compound interest, which again is an example of exponential growth. If you looked at maybe a visualization of this account balance at the beginning of this time, and he starts at $2,000, the growth is very minuscule, but as time goes on and the interest gets compounded more and more, the amount in that account grows exponentially. Remember, the other part of notes today is not just exponential growth, but also exponential decay. This is when something is getting smaller at an exponential rate. Looks very, very similar. It's still y equals a times b to the x power. The difference here being that a needs to be greater than 0 still, but notice b, the base, the growth factor, will be less than 1. Because things are getting smaller, we have a value less than 1. Very similar to what we said for exponential growth, exponential decay. The base, or the decay factor in this case, is 1 minus the percent of change. So instead of 1 plus the percent rate of change, it's going to be 1 minus written as a decimal. Again, everything looks pretty similar. Otherwise, y equals a times b to the x. A is the initial amount before anything changes, and then b is the base decay factor, which must be between 0 and 1. So just one quick example, not quite so complicated as compound interest. We're just looking at the population of a city that was 45,000 people to begin with, and it's decreasing at a rate of 2% each year. So notice we have 45,000 to begin with. It's decreasing by 2% each year, and it asks if the trend continues, what will the population be in 15 years? So as you see that formula up top, y equals a times b to the x. Remember from notes right back here, a is the initial amount and b is the decay factor. So a, the initial amount, should be pretty simple to plug in. That's going to be the 45,000. Now what we need to figure out is what our base or our decay factor will be. Notice it's decreasing by 2% each year. So just think about it this way. If I had 100% and now I'm decreasing by 2% each year, I now have 98% as far as what will be left each year with that decay. And again, we're not going to write that as a percent. We're going to write it as a decimal, 98%, 98 out of 100. So our base decay factor will be 98 hundredths, and then the last thing we need is the exponent, and this will be in 15 years, so that's going to be my x. So just plug in numbers in and then evaluating from there. Biggest thing you need to always remember is the rule of order of operations. We have to take 98 hundredths to the exponent first before we can do anything else. So I'm going to take 98 hundredths to the power of 15, and when I do that, I get a number that looks like 73,856, so on and so forth. So we're going to round this to a few decimal places, but I'm going to say 7386 when I round it. I'm going to round it to the 10,000ths place to try to be precise when I write this down in my work. Last step is just going to be to multiply that times 45,000. And again, I can just do that in my calculator. I can just type the multiplication sign and then 45,000, and it'll do it right away for me. And in your calculator, you'll notice you might have to do a little rounding because we're not going to have 0.6 people in our city's population. And so when I round this, I'm going to call it 33,236 people in that city after 15 years of decay. So just a couple examples of exponential decay and exponential growth. Big idea just being that you need to be able to plug in the numbers correctly and then need to follow your rules as far as order of operations and exponents. And that should take care of you for the rest of today. Good luck.